I'll just present my screen. Great. So yeah, thank you everyone for joining us today on this CCI webinar of November. This is going to be the last webinar of the year. We are going to discuss today carbon capture in geological formations, optimized by machine learning. So a very interesting topic. I hope we'll be able to discuss this very cutting edge application of machine learning for climate change mitigation, carbon removal, and capture. No, we have two great speakers with us today. We have Dr. Philipp Witte from Microsoft Research, Dr. Che Chang from Microsoft Research as well. They will tell us about the project with Northern Lights, which is a very pioneering project of carbon capture and storage. So I hope I will be able to discuss in detail how can machine learning be useful for this. We should be able to address questions for everyone at the end of the talk. You can just go ahead and write your questions in the chat at any moment, and we will go over them after we're done with each talk. No, so just giving a quick introduction to climate change AI. We are a global network of researchers, policy makers, entrepreneurs interested in applying machine learning and AI for climate change. And we as a community that organize digital events, events in conferences, for example, NeurIPS or ICML, and I also do research around the topic of climate change and AI. There was this foundational paper that actually started the organization, which is tackling climate change with machine learning. I invite you to take a look at it. We discussed many areas in which it could be interesting to apply machine learning and accelerate how we mitigate or adapt to climate change. We have also organized workshops in different machine learning and climate change conferences. The next workshop is going to be in NeurIPS in December 2021. We kindly invite you to register and attend the webinar. I think it's going to be very interesting. Also, there is a new thing we have, which is this community system in which you can discuss with people that are working in the area, find collaborators for work or for research, etc. And you can connect with people working on different topics related to machine learning and climate change. Also, there's a directory in which you can search for people, specific check areas of expertise, whether they're seeking, etc. There is also a wiki in which we summarize most of the contents of climate change and machine learning for different areas. You're invited to both check the wiki, but also contribute from your area of expertise. Finally, there is a newsletter that goes up each month, which I personally find very interesting. Lots of research, jobs in climate tech, funding, etc. comes there. So it's a lot of very interesting material, and just once a month. And finally, a very special announcement, which is we're organizing this climate change AI summer school, which will occur next year, and we'll have two tracks: one for AI experts to develop expertise in climate tech or in climate change applications, and the other one for climate change scientists and researchers who wanna develop their machine learning skills. No. So you are invited to apply. The deadline is December 17, 2021. It will be I think it will be a very interesting week in which you will learn a lot. We organized it last year, and it was a very good experience for people attending. So if you're interested in that, I encourage you to apply. Yeah, and then in our general webpage, there is a link to all of these things, and you can just check that to just reconnect with these opportunities. So yeah, without further ado, I would like to introduce our first speaker today, Dr. Philipp Witte. He's a researcher at Microsoft, working in a broad, I would say, like in industry-related problems, applying AI or ML. And prior to that, he received a bachelor and master's in geophysics from the University of Hamburg and a Ph.D. in computational science and engineering from Georgia Tech. So yeah, I will let Philip present his research today. Thank you.
Sounds good. Thanks, Felipe. I'll share my screen now. All good. You can see my screen, right?
Yep.
Okay.
Perfect. Thank you.
Yeah. Thanks so much for the introduction. It's really exciting to be speaking here. I saw a couple of familiar names in the chat. Some people from my time at UBC, for example. So nice to see you all again, even though it's only really virtual. But yeah, so like Felipe said, my name is Philip. I'm in a group at Microsoft that's called Research for Industry. I just want to say a couple of words about our group. So as you might be aware, at Microsoft, we have a very big research department that's called Microsoft Research that has, I think, about 1,000 researchers. And then we have our industry or our cloud platform where all our industry customers are. And the idea of our group is kind of to accelerate that technology transfer from Microsoft Research into the different industries that we work in. So those will be financial industry, agricultural industry, and the energy industry, obviously being one of the big ones. So yeah, so we work together with researchers from Microsoft Research. We also work together with academia, and we're really just trying to help bring the innovations over to our customers so they can leverage those. So we have a small-ish core team that's continuously growing, that's made up of researchers. We have software engineers, and we have program managers who kind of work with connecting us to the clients. And then, as I mentioned, we do have a whole bunch of academic collaborations. So specifically for energy and CCS, we have 3 collaborations ongoing currently, one with Professor Sally Benson from Stanford, one with Professor Felix Herrmann from Georgia Tech, and one with Professor Jared Gorman from Imperial College. And then every summer, we have a large number of really talented interns. So the work that we're presenting here today, both me and my colleague Jay did that work in collaboration with 2 interns, one from UT Austin, and the work I'm presenting was done together with Tu Gruel from Colorado School of Mines. So yeah, so in this specific project, we wanted to look at accelerating CO2 flow simulations for carbon capture. This was a project that was done in collaboration with one of our industry customers, clients, specifically the Northern Lights project. So Eric Skjetne, sorry for mispronouncing your name, Eric. He is the digitalization lead of Northern Lights, and we work together on this kind of incubating this idea, see how we can leverage AI for projects like Northern Lights. And then Ranveer is our general manager of our RFI group. I know Eric is in the audience too, and he really is the person, knows everything about Northern Lights. So I want to give a quick intro on that, but if you have any specific questions, he will be able to answer those much better. I'm really, I guess, just giving this kind of more from the Microsoft perspective. So the Northern Lights project is a open source CO2 transport and storage project, which is the joint venture between 3 companies, Equinor, Shell, and Total Energies, and it's also supported by the Norwegian government. And the idea of Northern Lights is to provide essentially the infrastructure to transport and store CO2 permanently, and then have customers who are basically capturing CO2, and then that CO2 is transported and stored through the Northern Lights project. So at this point in time, there are 2 customers in Norway. One is a cement plant, one is a waste to energy plant in Oslo. So the carbon is captured at those factories, is compressed, and then it is transported on a container vessel to a CO2 terminal that is in the process of being built in Øygarden, which is kind of at the top in the top figure here on the continental shelf of Norway. And then from that CO2 terminal, there's a pipeline that transports the CO2 to a injection site that's in the North Sea. So the carbon is then transported there, it's injected into the subsurface, and then stored there geologically permanently. And then at the beginning of the project is meant to start in 2024, and at first it's meant to store 1.5 megatons per year. And then over the various phases of the project, the second phase will be to store up to 5 megatons per year. So when we did that collaboration with Northern Lights, we wanted to explore, I don't know if I can remove this. We wanted to explore the role that AI and ML can play in climate science. So, I mean, generally in climate science, we would be interested to describe what's happening on the various aspects, I guess, of the Earth, the surface, what's happening in the atmosphere, what's happening in the subsurface, and what's happening in the ocean. And of course, all these processes that are happening are described by partial differential equations, just a couple listed on the lower right-hand side here, of course. And the conventional approach would be to kind of by hand develop numerical models to carry out all these simulations. But some of these equations are not only very difficult to solve, they're also very computationally expensive. And especially if you're interested in things like data assimilation or inverse problems, there's definitely a role that AI could play to kind of help us with all of this. So here we wanted to kind of compare what is the role of, or how do we leverage AI modeling today? So today, I mean, we mainly develop our numerical solvers manually by hand by having some scientists work on the physics, and then they kind of create some numerical solver. Typically, these solvers are really sophisticated. They have a lot of input parameters. They can do all kinds of things. They're very generic too, so they're able to really handle very different kinds of input, so that it really covers a very broad range of things you can do with them. But oftentimes it's kind of overkill, because then if you actually pass it on to the end user might only be interested in really using it for a very small range of scenarios. So now you're really building the super fancy race car that you're handing off to the end user, and the end user is sometimes a little bit doesn't really know what to do with it, maybe, or it's very complicated to use, and it also takes oftentimes a long time to run. So the role that AI can play from our perspective would be that you still need that first step. Obviously, you still need to know about the physics and develop your physics-based solver. But from there, you then go and derive basically AI-driven models that maybe they cover only a small subset of what your full numerical model can do. But it's kind of tuned towards a specific application, so that when you hand it off to the end user now, they're able to use a numerical AI-driven solver that's much faster, maybe only covers like a smaller range of capability, but it's okay, because typically you don't need all those capabilities that every solver has. So then obviously for different application, you would have to tune different models. That would be the idea behind that. Yeah, and then ideally, obviously, you would have the end user benefit from really large speedups. I know that it's not only in the work we did, but other people too report speedups of up to 1,000 or even beyond that. So that is really exciting. Okay, so I mean, the field of data-driven simulations is obviously a super hot topic. There's a lot of research going on. I just listed a couple of the main architectures that have become popular over the recent years, like neural ODEs, physics-informed networks, FNOs. So going back kind of to the Northern Lights project, what we wanted to do is, can we take one of these architectures and apply it to one of the problems that comes up in carbon capture, which is simulating the CO2 in the subsurface. And the reason why you want to do that, as I said, when I showed kind of the overview of Northern Lights, the idea is that once you transport the CO2 to the platform, you inject the CO2 into the subsurface for long-term geological storage. So there's a couple of questions that you want to be able to answer. One is, how much CO2 can I store in the subsurface? The second question is, how do I inject the CO2? For example, where exactly, at what rate, how much can I inject, over what time frame? And then maybe the most important question that's of interest, obviously, for the general public is, what happens to the CO2 after I inject it? Does it actually stay where it's supposed to be staying? Obviously, we're interested in the CO2 being permanently stored on like geological timescales and not travel back up to the surface. So the idea in this project was, with Northern Lights, explore, can we use data-driven simulations to actually simulate that? And there's already a range of work even in that space. So really any of these architectures listed here, most of them have been applied to fluid flow and specifically carbon CO2 modeling as well. Just a few works that I listed here. But kind of one of the things that's maybe a little bit missing from all this work is the question of, can we apply this to a very realistic model? And can we scale it to 3D simulations? So the architecture that we picked for this project is a neural network that was kind of made popular at the beginning of the year called Fujino operators. And I think taken off kind of now in popularity, so people might be familiar with them. Just wanted to kind of, I guess, briefly summarize the approach. So in the original paper, and the way we use it too, was just a purely data-driven approach, where the input would be parameters that describe the subsurface, like permeability of the rock, porosity, and the output would be a history, the saturation history of the CO2. So basically the heat map that tells you how high is the CO2 saturation, which really tells you where is the CO2. And these FNOs are interesting for two reasons. One of the reasons being that they're supposed to be grid independent, so you can learn an operator that is independent of your input grid. So if you have to really only train it once, and then if you change the grid, in principle, you don't have to retrain it. So that's obviously very interesting. The second reason that we picked FNOs is that it seems they work very well for describing partial differential equations. And the reason is that it's because you're operating in the Fourier domain, you're basically having a global operation as compared to kind of the conventional CNNs who work with convolutions and have more of a small spatial imprint, I guess. So you have to stack a lot of layers and able to really capture all that spatial context. Versus with FNOs, it seems that they work very well even for relatively small numbers of layers. Yeah, so in case you're not familiar with FNOs, it's a neural network that starts with an encoder where you basically increase the channel size of your input, and then you have a stack of these Fourier layers where in each layer you do a spatial and temporal Fourier transform. And then once you're in the Fourier domain, you basically throw away most of your data, and you only keep a couple of these Fourier modes, and then you learn weights, a linear operation, to weigh those Fourier modes, and then you go back to the spatial domain, you apply your nonlinearity, and then you kind of have one of these outside operations that acts in the physical domain. And you stack a couple of those on top of each other. So the question is maybe that, okay, what's stopping us really from applying that to large-scale 3D models? And I guess the answer is, as always, it's computational cost and it's memory. So if we look at the runtime of one of these FNOs, this was just with the code from the original paper, you see that you spend most of the time with the FFTs, which is maybe not that surprising because you have to do 2 of them in each layer. And if you're talking about a 4D problem where you have 3 spatial dimensions and a temporal dimension, then that would be a 4D FFT. The second part is you spend a lot of time on the memory allocation just because you're subsampling those modes. And then before you go back to the spatial domain, you have to zero pad your input and then go back to be able to apply that Fourier transform. So you spend a lot of time on that and actually less time on the actual convolutions or spectral convolutions. And the second part, memory too. Like I said, I mean, the encoder and decoder are just one-by-one convolutions, so they're not super memory intensive. But then in the Fourier layers, because you're doing this mode subsampling and then zero padding in every layer, and obviously PyTorch kind of just keeps track of all of that, you're keeping track of a lot of memory allocation that is not really necessary. So when we think about now, how can we actually scale these AI-driven simulations to relevant problem sizes, there are kind of 3 pillars of innovation that we need to think about. One would be on the network side, how can we innovate or make the networks more memory efficient, reduce the runtime? The second aspect will be around the training data generation, because we have to, or in this work at least, we decided to use training data that we generate with numerical simulators. And I guess there's a different argument too that you can make. Is that really necessary? Is maybe these physics-informed network a different, better approach? But in this specific case, we wanted to leverage existing simulators for CO2. So we have to run those in parallel in order to be able to generate training data. And then the third component that you obviously need to is once you have your training data, you have to do distributed training and able to fit your model and data sizes. So to address kind of the left-hand side of that graph, in terms of the network innovation, what we did is, if you look at the kind of the FNO architecture, one of the questions you might ask yourself is it really necessary for me to go back and forth between the frequency and the spatial domain in every of these layers? Wouldn't it just make sense to maybe only go to the frequency domain once at the beginning, stack a couple of layers in the frequency domain, and then just go back once at the end? So we tried doing that, and then you quickly run into the problem of having to apply a nonlinearity in the frequency domain, where if you just kind of do the most obvious thing and you just do like a nonlinearity on the real and imaginary component, you realize that doesn't work very well. And there are even some different alternatives for frequency domain activation functions. And we tried a bunch of those, a couple of whom are just plotted on the right. And they don't seem to work that well either, which was interesting for us. So the question is, can you introduce nonlinearities differently? And the answer is yes. Obviously, you don't have to have a linear layer. If you just have a quadratic layer, you apply a quadratic operation to your modes, then you don't need that nonlinearity anymore. So now, instead of having a linear operation with a nonlinearity, you just stack a bunch of these quadratic layers. And in our specific architecture, we also have a little trick so that you avoid that your number of weights actually grows quadratically. The number of weights, even in the quadratic layer, still grows linearly, just with a higher constant than in the original formulation. And then this plot on the right, we basically fit a single training example from the original paper, from the Navier-Stokes example. And you can see that the original FNO is in blue. And then if you go to this frequency formulation where you try to use some activation function in the frequency domain, it doesn't work very well. Versus then if you introduce these quadratic layers, you get a really good data fit. Just to talk briefly about the memory, if we compare the memory consumption for a single layer, FNO layer, versus a single of the quadratic layers, then you can see as the number of modes that you keep as a percentage of your number of grid points grows larger, so you keep less modes as a percentage of your whole image, you see that the memory consumption becomes much less than the FNO. So in the original paper, for example, they had a 64 image and they kept 8 modes, so that will be 1/8. So in that case, you use significantly less memory. If you go even larger, then the memory saving becomes even better. If you stack a couple of these layers up now, the benefit obviously becomes a little less, because in the first and last layer, you still have to do basically the mode subsampling and the zero padding. So that becomes a little less, but it's still about half or less. And then the more layers you stack, obviously that advantage becomes bigger again. So if you stack 8 layers, your memory savings become larger again. Okay, so this may be just a quick excursus. Before actually going to the CO2 example, we applied this network formulation to a little bit different problem type, which was interesting for us because it's a very complex problem for neural networks to capture, where you try to fit or simulate this Wi-Fi response. So this is a very highly oscillatory signal that's also pretty high frequency. So that will be something where you expect that typical FNOs might maybe not work that well. So the idea is that you have apartment layout and you have different location of your Wi-Fi router, and you want to estimate or figure out what the Wi-Fi magnitude is. And that is a problem that's actually inspired by a blog post that we read from Jason Cole, which is super cool. If you haven't seen that, you should definitely give that a read. Yeah, so here we compare kind of the conventional FNO with 4 layers versus a quadratic FNO, also with 4 layers, and the number of modes was also the same in both example. And you can see that the quadratic FNO gives you much better or high result in terms of signal to noise ratio. Then, okay, here we look compare a little bit different architectures. For example, can you make the FNO better by using a larger number of modes, or can you make the result better by stacking more layers on top of each other? The answer is yes, but still it's not as good as the quadratic one that only has 4 layers and 32 modes. And then if you look at the runtime memory and SNR, you can also kind of see that the quadratic formulation is faster even than the FNO with the same number of layers and modes. Uses less memory and always gives you higher, better quality results in terms of signal-to-noise ratio. Okay, so back to CO2 now. So CO2, last example, we solved the Helmholtz equation. In CO2 flow, we're solving multi-phase flow equations. So this would be kind of the equation on the right. And I'm actually not a reservoir simulation specialist myself, so this is all new to me too when I looked at this. And I just kind of realized it's very complicated. I mean, there are all these solvers for two-phase flow that are super complicated to use. So we're pretty lucky to have people like Eric and people in his company kind of help us figure this stuff out. But yeah, so the idea is that typically you would solve these multi-phase flow or two-phase flow equations where by multi-phase, I mean that you simulate how different fluids interact in the subsurface. So in this case, you would simulate the behavior of 2 fluids or phases. One of them is obviously CO2, and the other one would be salt water, which is also called brine. And that is the fluid that is present in the subsurface before you start injecting the CO2. So you have salt water in the subsurface, you inject CO2 now, the CO2 displaces the salt water, and then you want to see what happens to the CO2 after I inject it. Okay, so as I mentioned, in the architecture that we use, we just use a fully data-driven approach. So we map these reservoir parameters directly to the saturation. I know that people started looking at these FNOs also in combination with these physics-informed losses. So that's something I think you can probably do on top of that too, if you wanted to. Just in this work, we did not do that. This is now kind of the second column that I wanted to address about generating training data. So since obviously I'm from Microsoft Azure, we use Azure or cloud platform to simulate the training data in parallel. And the way we do that is we use a distributed programming framework written in our group called Redwood, which allows you to basically run parallel workloads on Azure on top of one of the cloud services for batch computing. So you can basically set up a Jupyter notebook where you say, okay, this is the code that generates my different models. And now I want to run different instances of my simulator with different input parameters. So you set up a Docker container that has a simulator. In our case, we use a simulator called Open Porous Media or OPM, but you could use a different one as well. And then the training data that we generated, like I said, we tried to pick something that's fairly realistic. So we took an existing model that's open source. It's called the Sleipner model, which is from an earlier CO2 project that was also done in Norway. And we took the original model and generated random permutations of that model, or more specifically of the permeability of that model, and then simulated the separation history for each model using the Open Porous Media simulator. And we ran 1,000 of these simulations in parallel. Depending kind of on the input size, the simulations take between 15 to 30, 45 minutes. So yeah, it's not something you want to simulate on your laptop, I guess. So this is where it was definitely helpful to have these batch computing abilities. Okay, so we trained this, the FNO and the quadratic FNO with 1,000 training examples. The dimension of this model would be a 32 cube and the number of time steps is 24. So after we're done with training, we have a new set of models, of test models that was not used for training and was not used for validation. So here's just one of those random permeability models that we generate, and then we compute the saturation history with Open Porous Media. So Open Porous Media on the left, then the standard FNO, you can see it looks overall not too bad. There's some deviations, especially at the end or in the slice that you can see. Generally, we found, I mean, first, obviously, we did these simulations in 2D plus time, and there everything works much better. So things become much more difficult once you go to 3D, which maybe that's obvious, but it wasn't necessarily obvious to me. because you could also argue that, okay, now I have an additional dimension that has additional information that I can use to basically still learn the same relationship. So maybe that would help me to basically learn this two-phase flow if I have that additional information. But just the training process and I guess the local minima that you encounter, all this makes it really more challenging in 3D, or I guess it's really 4D because you also have time. Then with a quadratic FNO, the advantage is maybe not as distinct as the Wi-Fi example, which is of course why I showed the Wi-Fi example too. The quadratic FNO in most cases was still better. The SNR is a little better and it has a little bit less of that noise. Just kind of to be transparent, I'll also take the example where the other, the conventional FNO works better. So this is a different realization of a model. FNO on the right now. And then QFNO on the right works a little bit worse actually at this point, in this specific example. Yeah, training convergence on the left, fitting the training data was much better with the QFNO. So the fact that it kind of performs similar at the end tells you that there are some issues with overfitting that we're still trying to address. If you look at the speed up now, obviously the speed up is really large for evaluating these FNOs with respect to the original simulator, which there's only an implementation on CPU available, so we cannot get a number for GPU. And then if you kind of compare the best case of simulator and CPU versus neural network on GPU, then you end up with speedups like 1500, which is obviously really impressive, but obviously you should take that kind of with a grain of salt, since it's not, maybe you could argue it's not a really fair comparison. On the other hand, you kind of compare the best available version on both architectures. So you could argue, okay, that makes sense to compare. And then just really quickly, I briefly touched upon this at the beginning, that one of the big promises of the FNOs is that you can train them on you can run inference on a different grid than the original training. So in this example, we trained the FNO on a 64 cube, which is roughly 260,000 grid points, and then try to really scale it up as far as we can and run inference on a 512 cube. So in this case, you don't really get any more details. So the question is, does it actually give you really more insight? But so that's kind of still future work, but just apart from that fact, the fact that you're actually able to run inference on a 512 cube for CO2 simulation, I think that's pretty impressive. There's probably not a whole lot of simulators out there, like real existing PDE simulators that can run at that scale. Okay, and just to kind of put that into perspective, if we normalize the number of grid points with respect to the Sleipner model, then the training that we did was 0.1 of that, but the inference on the 512 cube would be 68 times as large as the Sleipner model. And the Sleipner model is like a real world case study. So if you're able to even use this on a smaller scale, I mean, that would definitely be industry scale or a relevant problem size to work with. So that's pretty promising. It does look like we can actually train these networks on problem sizes that will be relevant. Okay. I'm running out of time. Just quickly, what's next is scaling the model beyond a single GPU. So what for now, we only did data parallelism, where we still have to fit a single model on a single GPU. And you kind of max out at about a 64 cube. That's really all you can fit. If you want to go beyond that, you have to do some kind of model parallelism. Here we're kind of doing two collaborations, one with the Microsoft DeepSpeed team, who have a framework that allows you to do that, and one collaboration with Georgia Tech that is using a framework called DisDL. And then the second aspect where we want to look at is obviously to go to more realistic physics, because we did a lot of simplifications here. And the question, for example, does this generalize to multiple wells? And if you vary the well location, which we kept all this information fixed now, the question is if that generalizes, or to what extent does it generalize? That would be very interesting to find out. Yeah, so many thanks to you for all your attention. Thank you for everybody, from my colleagues at RFI, the companies that we work with, Philipp for organizing. And then last, I just wanted to point out that we, every summer, like I said, have summer internships. So I encourage you to check out the website of our group, kind of keep an eye out for opportunities. There might be full-time opportunities from time to time, but definitely there will be summer internships for this summer. Thanks, and I'll hand it off to my colleague, Chip.
Thank you Thank you, Philip. That was very interesting. So I will just introduce Chem. I will share my screen. All right. Great. So yeah, before this, I will invite you to write any questions you have in the chat, and we will go over them at the end of the talk. Ideally, want to leave, I think, like 10 minutes or so at the end of this for questions, or 5 minutes at least. Yeah, so we're going to move to the second speaker, Dr. Che Shang, which is he's a principal data and applied scientist at Microsoft Research, and did a previous Ph.D. in geophysics. So I will just give the floor to Dr. Shang. Let's see. Oh, I see. Just technical issue. All right. Che, you should be able to share your screen now. Sorry about that.
Yeah, so now I can be able to share my screen. Can you hear me?
Yeah, we can hear you.
Yeah, thank you. And welcome to the presentation of automatic detection of potential leakage pathways for subsurface CO2 sequestration. So can you also see my mouse?
Yes, we see it.
Okay, so the potential leakage pathways here refer to geological faults that can be weak zones that can lead to potential CO2 leakage from the subsurface storage site. So this work is a collaboration between Equinor Northern Lights team and Microsoft. And my name is Che Zhang here. And Harpreet is a summer intern with Microsoft who contributed primarily to this work, along with expert geologists and from the company Equinor who shared the Northern Lights open dataset with us. All right, let's start with the concept of the CCS, carbon capture and storage. The purpose here is to reduce the carbon footprint and help tackle global warming. It's a three-step process, including capturing CO2 from power generation and other industry activities, and then transporting CO2 to the site of storage, and the last injecting it in the underground geological formations and storing it in a deep reservoir permanently. So CCS is necessary for us to achieve 50 to 80% emission by a reduction by 2050. So without the CCS, it's hard to reach that scale. It's really important. And this slide would explain why potential leakage pathways or faults would pose a risk to the subsurface CO2 storage or containment. So in CCS, CO2 is injected and stored at least 800 meters below the surface, and we want to contain it for 1,000 years. Like the saline formation or the depleted oil and gas fields are great candidates for CO2 storage. At the same time, impermeable cap lock is also required for trapping the injected CO2. But some like potential leakage pathways or fault could lead the CO2 to migrate across fault or along the fault to the surface. And that's why it's really important for us to understand the potential leakage pathway force in the storage reservoir. And because any leakage would cause the CCS project to fail. And especially we want to keep CO2 there for a long time, 1,000 years. So CO2 containment risk assessment is crucial and mandatory. And we'll see here a 2D line of a seismic image from a 3D seismic volume. And the top layer is water layer is offshore in North Sea, and beneath that you'll see the layers or horizons are the reflection of geological formations captured by seismic. And the vertical axis represents the depth. And you'll see there are also many faults in this seismic image. So the faults are the fracture zone separating two blocks of rock, and where the two blocks are moving relative to each other. For example, along this fault, the left block is moving down. So those faults could be weak zones and could potentially be leaky. And to understand the geology and typically this would require interpreters to digitize and map all the horizontal faults, and which is shown on the bottom. You will see that the current northern light pocket of the CO2 storage is plotted in this blue circle. And in this area, you look at the seismic image, there are so many faults around it, above it, and in the overburden. So these require very detailed digitization mapping of the faults as shown in this section. And imagine this is a 3D mapping could take interpreter weeks to months for this long time work. And we here want to develop a deep learning method to efficiently and accurately map all those 3D faults within the 3D volume, and to accelerate the process. So we want to follow the computer vision technique, the convolutional neural nets idea to the problem. So what you're seeing in here is the photo on the left, and by using CNN we can, or segmentation, we can decompose that into a number of classes, and with that we can also apply the same semantic segmentation to seismic image. On the left is a 3D training data set, and with the CNN applied, we can decompose that into two classes. And so this is a binary classification for every voxel in this 3D volume. So label 1 indicates fault, and 0 indicates non-fault. So with this supervised learning, we hope to map the seismic image to its corresponding labels, two classes on the right-hand side. So there are many studies in this area. We are not the only one, and the training data set and labels shown here are borrowed from Wu for this for detection work. So overall, you'll see that the training data set here is relatively simplified. The fault planes are straight lines, and the horizons and the fault geometries are also not representative of complex geology. And so instead, we created a package in-house for generating a complex synthetic training data set. So there are 6 steps. We start with a layer cake model, a 3D model, and then we folded the 3D model with a number of folding functions. And after that, in step 3, we add the shearing into that and make it even more complex. And after that, we start to add in faults and to shift blocks along the fault relative to each other. And after that, we convert the image with the wavelet, and after that, we add noise and run smoothing. So this gives an idea of the synthetic data generated from this 3D cube. And we pull out inline and cross line. So in this X direction, we have the training data, 2D display, and the corresponding label of faults. And also in the Y direction, we have training and data, 2D display, and the corresponding label. You'll see the fault planes here are more complex. They are curved and they may be truncated, and they are interacting with others. And this also gives your idea about how multiple sequences can be generated in the synthetic data to mimic complex geology. Again, we started with the layer cake model, flat horizons, and then we run folding phase 1. And you see now we have a certain anticlines, and then we can add faulting into the synthetic data, creating fault planes, and then we can add a second folding sequence after the first folding sequence. You see the second folding added on top of the first folding, and then we can add folding again, and the sequence, it can be one or multiple faults in this for the 2 sequence. And this process can iterate and would make the training data more realistic to mimic the real geology. Next shows a 2D display of a 3D training data cube with a seismic on the left and the corresponding label on the right hand side. You see very complex geology here, and in certain areas you will see very dense faults clustered in a small region, and in certain areas and the faults are sparse, and the fault planes are curved and with various dips, and they are interacting with each other. So this is a complex training data to mimic the real geology we see in the seismic dataset. On the bottom is the displacement field, a 3D field, and for 3 directions, X and Y and Z. So imagine this seismic cube is generated by a number of warping steps or distortion steps, and we started with a layer cake model. So imagine with that model, and there is a final cumulative warping field or displacement field. If you apply that displacement field, that would give you the final generated synthetic cube. So and the idea here is with this displacement field, if we apply the displacement field to the original flat layer model, you're gonna get the synthetic training data set. And in a similar manner, if we unwarp this generated synthetic data with the displacement field, we are gonna get the flat layer. So this displacement field keeps a record of the geological deformation of the formations, and it would help us understand the geology, and by training this this mapping relationship from the cube to the displacement. This would help us map the horizons and understand the geology history. So the synthetic data generated here are fresh, and we have not had time to use them for training yet. So the study in the rest of the presentation is based on the public training data set provided by Wu. So with the training data set on the left and the corresponding label on the right hand side, with the labels all labeled with the input image. This is through UNet. We're started with that. So it's through a number of down sampling steps and then up sampling with a shortcut connection connecting the decoding to the encoding to the decoding part. So this would the UNet structure would allow extracting features from multiple resolution and to derive the fault prediction here.
Hi, Chem.
Yeah.
Let's just wrap up in the next couple minutes so we have time for questions. So you could just go a little faster with the presentation.
Yeah, sure.
Thank you.
So here's the prediction on the validation dataset. You will see the prediction labels are pretty close to the true label here. And after that, we are gonna improve the CM model with the data augmentation and etc. Here gives an idea. We use a elastic deformation field applied to both the training data and the labels to enhance the generalization of the training data set. So with that, and we can apply to the training data set to make more complex fault geometry here. And this curved faults represents those complex fault plans in the real world. And when we apply that improve the UNet, you will see improvement compared to the original preliminary UNet with the increased precision and the recall numbers. And we also take advantage of the deep lab models using these choose convolutions to enlarge the field of view of the filters, but not to increase the number of parameters. With that, when we apply to the validation dataset, we see better prediction, for example, in this area compared to the UNet for this example, and we see better precision and the recall too. And now we want to apply this to the field data, the real data set in the northern lights. So the cool part here is that we only train the CM model on synthetic data set without any human labeling, and then we apply to the real data set, and this is the study area, and we compare the preliminary UNet versus the improved UNet. We see better prediction at the yellow arrows, and then we compare UNet versus deep lab. We also see improvement with the deep lab for a number of the yellow arrows. And our best result comes from the combination of the UNet of sampled grid together with the deep lab. And the green arrows indicate areas where the faults are predicted more accurately compared to the missing part on the left. So also a depth movie showing the prediction throughout the 3D volume, and which only took less than 7 minutes versus human picking probably taking around a month. So this dramatically reduced the picking time. All right, summary. So our automated 3D fault picking using CNN significantly reduces the interpretation time for the CO2 containment risk assessment. And the deep lab model, and also with the generalization techniques, performs better than the original preliminary unit. And our CM model is trained only with the synthetic data, and it can generalize to various field data sets. So we applied it not only to this northern light data, but to a number of other data sets, including Gulf of Mexico and Netherlands. And due to data permission, I have not shown them here, but it generalized well to the real data set. And acknowledgement to Microsoft, Equinor, and the organizer here. Yeah, thank you for attending, and happy to answer questions.
Thank you. Thank you very much. That's a very interesting talk as well. So right now we're gonna move to questions. We have a few minutes, so I just gonna ask two questions that just pop up in the chat. With first one, it has to do with the impact of this research. Maybe we can comment what could be just the general impact of this kind of machine learning models to make these projects feasible, or even to make these projects reliable in terms of later being finance or sell offsets or carbon removal credits, for instance. Philip, do you want to comment on that?
Sure. I was just wondering if we have still Eric with us, if he wants to make a comment, since he was the person from another. I don't want to put him on the spot. Just if Eric, you want to say something, please. But yeah, I mean, these AI-driven simulations, from what we heard from clients that we work with, have a huge impact for them, because they definitely say, look, we have all these simulators, but they're so complicated to use and it takes such a long time that there would be definitely a benefit for having these AI-driven simulations that this could actually be used in production. Of course, you have to answer all these questions does it generalize? Is it worth the upfront cost of training versus the speed up that you gain afterwards? But if you have some of these projects like Northern Lights that run, I mean, the monitoring, you have to do that for decades. So if you tune your data-driven simulator once, I mean, a couple of things are going to change, but the geology is not going to change. The number of wells probably also not going to change. So a lot of things are going to stay in place, so that might be worth it. And sorry, what was the second part of the question?
Second part is just from the financial perspective, right? Maybe if you give more certainty about avoiding leaks, for instance, that will be the project's more feasible. I think Eric wants to make a comment.
Yeah, it's a lot of subsurface work that goes into a CCS project in, for example, Northern Lights or Equinor or anywhere. So I think people are not aware of how much work that actually goes into this. It is thermal simulations, it's flow simulations, it's rock mechanics simulations, it's a lot of uncertainty assessments, risk assessments, etc. And on the top of that, you have also this seismic monitoring from time to time. That are very costly experiments running with streamer seismic, and so it costs at least some 100 million Norwegian kroner per experiment. So it's and that is the kind of the proof of the pudding. It shows where is the CO2 after you analyze it. So, but of course, beyond that, you cannot do much, as Philip also commented on, that if it should stay there for 10,000 years, none of us will really be able to check it.
Yeah, thank you. Yeah, that's a very interesting point. I think it puts in perspective the difficulty of the problem, and the complexity of the problem. The final question would be, just to close, is in terms of generalization, do you want to generalize to other locations, to other timeframes, or we want to be very good on this specific reservoir, for instance, Northern Lights?
I mean, and Shay can comment more on the seismic part. So for the reservoir, I think for a start, it would already be good if you could just generalize for a fixed location. It might be too much to ask to generalize to a very different type of geology. I think if you train a different models for, say, different locations in the North Sea, that might still work. I don't think it's going to work for train on North Sea and use it for Gulf of Mexico. I think it's just too different. But like I said at the beginning too, I think it's too much to ask to say I want to generalize to everything. And it's more of a fundamental, I guess, conversation that also people in the natural language world have. Should you train one giant model that does everything, or do you train a couple of small models? And I think it's the same here. It's just going to be much harder, obviously, to train. And can you rationalize the cost of training one super network that does everything? I would be a little bit hesitant, but I would love to be proven wrong.
Yeah.
And the usual work of the reservoir engineer is to actually add wells, to change well locations, to see what is the optimal injection point in the reservoir, where you can get most capacity of the reservoir you have, and so on. So I'm very eager to see if you can just move the well 100 meters to the side. Will it still work? You know.
Yeah. So for the fault detection work, the advantage is we can generate various geometries using synthetic data. So overall, in the first order, the model trained with the synthetic data typically generalize it well to a number of different real data sets across different regions. So to be more accurate, a local model may be further adopted for, but overall, by examining the performance, it can generalize well enough to different field data from different regions.
Great. Yeah, thank you. So we are unfortunately we don't have any more time. There's a couple more questions in the chat, but yeah, like hopefully we were able to address them, like messages to the speakers, or feel free to just like yeah, or contact me, and I could like ask the speakers about it too. So, but yeah, thank you everyone. Thank you, Philipp, Che, and Eric for your great points. I think it's very interesting research. I'm looking forward to see where this goes. I think it will be amazing for like just capturing like industrial emissions, no? Like emissions are very hard to decarbonize. I'm very excited by this research. So thank you very much. Everybody have a great day.
Thanks, Philippe.
Bye-bye.
Thank you. Take care.